paranoid. Let me check a third time. Okay. Yes, the number's going up. Okay. All right. So, welcome to the exam review. It may not be as exciting as you think, but what I'm going to end up doing is I will stress that what you have on the worksheets is going to very closely reflect the topics that you're going to see on the exam. I will specifically point out certain things that may be more likely to show up on the exam than other things. So, to start with, I'm going to look at the chapter 1 and 2 stuff. And very first, and I will add some detail as well, is the intermolecular forces. The strengths, the relative strengths of your intermolecular forces will be the first thing. So, in fact, I will write some stuff down right now. So, again, let me know if I write off the page. The very first thing, strengths of intermolecular forces. Okay, so the intermolecular forces you learned in class are ionic, hydrogen bonds, dipole, 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 induced dipole, and the last one is induced dipole, but it has another name or a couple other names. London dispersion and van der Waals also show up here. So make sure you recognize any of these possible names for induced dipole. So London dispersion and van der Waals. Okay. Now the relative strengths of these things compared to each other actually follows as I've drawn it here, where the strongest is up here, the strongest of your weak intermolecular forces, and the weakest of the weak is down here, which is the London dispersion, van der Waals, induced, whatever term you want to use. Yes?
So ionic is the strongest
of the weak intermolecular forces. I know it's weird. Yes. And I know you guys are thinking of like salt, sodium chloride. Isn't that a strong intermolecular force or something? What I mean by ionic being a weak intermolecular force is like, for the example, is from two separate molecules where they're not directly touching each other. That is where it is an intermolecular force. You can call it weak or strong. That part actually doesn't even matter. It's the relative strengths that matter. Ionic is stronger than everything else listed on this list here. Okay. Let's see if there's anything else to give there. Yeah, examples of each one. So, an example of an ionic interaction would be something like this. This is supposed to be a hydrogen, my bad. Between a carboxyl group and an amino group that are not directly connected to each other, they just happen to be in the same neighborhood, that will be an ionic-like interaction. Hydrogen bonds, you should know that what determines a hydrogen bond is you must have hydrogen attached to something that is very electronegative. There's only two options in biology and biochemistry. The hydrogen has to be either connected to an oxygen or it must be connected to a nitrogen.
And what about acid?
In biology, there is no hydrofluoric acid. So in biological systems, there is none of that. So sulfur is not strong enough to make a hydrogen bond. Good question. It's only OH or NH. If you had SH, that is enough to be a dipole. So you can have a polar. You can do dipole, but SH you can't do hydrogen bonds. Okay. All right. So dipole is between two polar groups. So, you know, I can make like a carbonyl here and maybe another carbonyl here. If you want practice on identifying polar functional groups and everything, I gave a very, at least I hope, a very specific breakdown of how to identify if a particular molecule you're looking at is polar or non-polar. Feel free to email me if it's not clear at any one of those parts. But the main part they will be asking for on the exam is they'll give you a bunch of different molecular interactions, or they'll give you the names of these intermolecular interactions, and you got to either give me you got to order them either from weakest to strongest or strongest to weakest, depending on what the question says. So this is the first thing you guys should study, is how to identify any of these intermolecular forces and order them as shown here. Any questions on that first part? Okay, yes.
So if we see on the test van der Waals, assume that it's on this definition.
Yes, yeah, even though, technically van der Waals is all three of these. For this exam, whenever you see the word van der Waals, pretend it's saying induced, or London dispersion, yes.
Alright, so dipole, that's the interaction between two oxygens?
Two polar groups. So yeah, technically between two oxygens in this picture here, but I will give an example where that is not the case, and that would be between O2 and O2. For those studying or remember some general chemistry or organic chemistry, what is the only type of intermolecular force that will exist between these two? It'll be van der Waals. It'll be induced dipole, because O2 is nonpolar molecules. They're individually nonpolar molecules, and that's because although oxygen is quite polar, they cancel each other out. So they act as nonpolar molecules. And again, look at the answers that I wrote down for the chapter 1 and 2 worksheet that'll explain that. Yes?
Is there ion dipole?
That technically exists, but you won't be given that on this exam.
How about covalent?
Covalent would not be a weak intermolecular force. Covalent would be, there are words they use, they would use intramolecular or supramolecular, I've seen sometimes. That is what a covalent bond is. It is very strong, and it is, unfortunately, there's debate with what is stronger, ionic or covalent. So for this class, if that ever shows up, and I don't think it's on the first exam, it might be on the final though, ionic beats out covalent, annoyingly. Ionic beats out covalent, but covalent beats everything else on this list, in fact. That won't be on the first exam. May show up on the final, I don't know yet. Ionic is stronger than covalent. Covalent is stronger than everything else. Okay. Other questions? All right. Yes, you got a question?
So how is ionic stronger than covalent?
Again, in actual scientific debate, they're about the same. So, but we have to pick one stronger than the other for the purposes of this class. I can't come up with a reason personally why it's stronger, but just for ranking, rank ionic stronger than covalent. All right.
What is intra and supra?
Yeah, oh yeah, intra and supra. So intermolecular forces are when the two groups you were talking about are not directly connected to each other. They're kind of just in the same neighborhood and they're interacting indirectly. Intramolecular and supramolecular means that they are within the same molecule. So both of these would be a covalent bond, like carbon directly bonding to oxygen. That is a covalent bond. But up here in this example, with the carbonyl here and the carbonyl here, they are not directly bonding to each other, so it's intermolecular up here. Inter up here, down here, because they are directly connecting to each other, that's either one of these terms would work, intramolecular or supramolecular. Yes?
So how do we distinguish for like NaCl, whether it's an intra or
You won't be asked that because ionic is, again, we keep running into ionic is its own special thing. You won't be asked if ionic is intra or inter. The only time ionic will show up is in these ranking type questions. All right, good. Let's move on to the next topic. I wanted to order these in the same order that follows in your notes, but I forgot to do that, so I'm going to jump around slightly. The next thing is in the Chapter 1, Chapter 2 section here, and it is you have to figure out, you have to know what determines the buffering capacity of a buffer. Somewhere, one of your practice exam questions, there's something like, which of the following is the strongest buffering capacity, or which of the following is the weakest buffering capacity? The only thing you need to know about that, and if you're answering the practice exam questions, you may figure it out. What determines the strength of a buffer, its ability to buffer reactions, is just how much concentration it has. The greater the concentration, the better its buffering capacity, simply because there's just more of the buffer. That's what that means. The weakest buffering capacity, therefore, is whichever one has the least concentration for that. Yes, question?
So like the higher the molarity, right?
Yes, the higher the molarity. Like, you know, if you had two to compare to, 5 molar versus 0.1 molar, the 5 molar buffer will be a stronger buffering capacity. No matter what buffer it is, it will be a stronger buffering capacity. And Reminder, what buffers do is they resist changes in pH, which is extremely important in biology and biochemistry. We want most of our reactions to occur around a pH of 7. So we have a bunch of buffers in our body that help this maintain true, that we help stay around a pH of 7. So that's what the purpose of a buffer is to stabilize pH and prevent it from jumping up and down too much. Okay. Let me see if there's anything else with buffers. Oh yeah, one more thing with buffers. Buffers are made of weak acids and their conjugate bases, right? So let me write that down here. Buffers are made of weak acids and their conjugate bases. Make sure this is still recording. Good. Are made of weak acids and conjugate bases. So because they're made of weak acids, different buffers are going to have different pKa's associated with them, right? Each one will have a different pKa. How do you know if your buffer is at its optimum pH? And the answer is, so in other words, we have different buffers in our body. They work better than others depending on what environment they're in. A good buffer that is at its optimum activity will be when its pH is approximately the same as when the pH of the environment is approximately the same as its listed pKa. Okay, so if you're given a list of buffers and you're given a list of pKa's, figure out what pH is best to use for which buffer. It's literally just match the pKa to the pH in the question. Okay, yes?
So is that like only at the isoelectric point, or is that like?
For buffers, you don't have to worry about isoelectric point. Buffers are just any version of a weak acid and its conjugate base. You won't have to worry about that.
So like phosphoric acid, you have what, like 3?
Yeah, phosphoric acid has 3 different pKa's, so it's good at 3 different places, at 3 different pHs. Yeah. Mm-hmm.
So, for example, if the pH of the solution was like 6,
Mm-hmm.
then a buffer with a pKa of
As close to 6 as possible will be the best buffer to use in a pH of 6. So the question is, for those listening to the recording, is that if you have a pH of 6 and you have a list of buffers which are a bunch of different pKa's, which one should you pick? You should pick the one whose pKa is as close to 6 as possible. What happens though if instead of pKa's, all the buffers are listed as Ka's? What do you do? So this goes into my next topic, is there's a list of equations you should know, and you should know how to use. A lot of them look very similar to each other, and that's the following. So, if I'm given a Ka, I can figure out its pKa by doing the negative log of it. So very similar to in general chemistry, this formula is the exact same formula as negative log of hydrogen ion concentration is equal to pH. So if you're given Ka's instead of pKa's, don't panic. Just type them into a calculator like so, and you'll get your pKa there. All right. So you know we can extend this some more just for the heck of it. So you know if I do minus log of OH, what does that tell me? EOH, exactly right. And if I do minus log of KB, the only one that's missing here is, this ends up being PKB, exactly. Okay? So, honestly, this isn't too bad. You memorize one of these and you can kind of memorize all of them, right? Because they're the exact same formula. I'll add 2 more so we can relate them to each other. And that is, when you do pH plus POH, you end up getting 14. And if you do pKa plus pKb, you end up equaling 14, okay? There's technically 2 other ones. I don't prefer to use these equations, and you won't have to use them, but if you see these equations on the exam, know just what they mean. You may not have to use them. And that is the following. Hydrogen ion concentration times OH ion concentration gives you, they write down Kw. Okay? All Kw is the mathematical number of 1 times 10 to the minus 14. Okay? So it is a constant, just like pH plus POH is equal to 14. Hydrogen ion concentration times OH ion concentration equals 1 times 10 to the minus 14. Anyone want to take a guess what Ka times Kb will be? 10 to the negative 14 again, exactly. So notice, there is, if at first you're looking, 1, 2, 3, 4, 5, 6, 7, 8 different equations, but in reality we kind of only have 3, right? That one,